the second lecture of Chapter 8. Super exciting. So last lecture we covered a lot of ground, and now we're ready to keep kind of rolling into starting to draw molecular structures. So the last chapter really kind of focused on looking at bonding trends that we already knew, but then seeing them more in depth from the perspective of what exactly is happening at the atomic level. So this periodic table here is trying to show the relationship between the columns of the periodic table and valence electrons, right? So valence electrons is something that we talked about in the last video, as well as the final video of our Chapter 7 material. So valence electrons are those electrons that are involved in bonding. They are also the electrons in the outermost in level. Okay, so let's just look at our group 1A, the alkali metals. If you think of, let's just do like potassium, right? If we were to write the electron configuration of potassium, we could just simplify it with argon plus our 4s1, right? And that would be potassium. If we wanted to do cesium, it would be xenon and 2, 4, 6, 6s1. So notice they both have just one electron in their valence shell. And it's only the valence shell that's going to be involved in forming our bonds, right? So here, if you were to write out all of the electron configurations, you'd find that this is going to be like S1, whatever the N is, right? So let's say NS1. This would be NS2. This would be NS2P1. These guys would be NS2P2. These would be NS2P3. Group 6A, NS2P4, and 7A would be NS2P5, and then of course our halogens, everything below helium, would be NS2P6 with that complete valence shell. So what's important is, as we've already talked in this class numerous times, is we have the same chemical behavior in species that are in the same column. And now we have this new understanding that that chemical behavior is due to the electron configuration, right? So in group 1A, we have one valence electron. In group 2A, we have two valence electrons. This is 3 valence electrons, 4, 5, 6, 7, and 8. It's really convenient with a lot of periodic tables. They'll go ahead and just have this designation of 1A through 3A that also is going to correspond to our valence electrons. So it's really nice periodicity, as we've seen throughout this entire semester. Periodicity is pretty awesome. The periodic table is just a really incredible tool. So just to kind of recap there, we have 1A through 7A written here. This N is like a little redundant, but that's okay. So regardless of what row of the periodic table you're in, if you are in this group or column, you are going to have this number of valence electrons that are, again, going to be those electrons involved in bonding. Oh, sorry. My controls, for whatever reason, like flipped to the opposite side. And it's just an old brain working at this point. That's not fair. Anyway, so one of the things that we really focused on in the last lecture, it's kind of like an episode. It's like an episode to a show that you never wanted to watch. but it's all good. We're here. We're having a great time. Okay, so the real kind of takeaway from the last lecture, one of the takeaways, was that bonding gives noble gas configuration. Right, so here we have 1 valence electron, 2, 3, 4, 5, 6, 7, 8. Noble gases have 8 valence electrons. We call that a complete valence shell, also known as 8 valence electrons, or an octet. Complete octet. So if you look here, we have group 1A. These are our bonding trends, right? So hydrogen tends to, in our ions, right? This is our ion trends. Hydrogen will lose one. Will lose 1 electron and just become a proton. This is H negative. Oh, I guess, okay, so you can have the hydrogen anion also, which would give the noble gas configuration of helium. Less common than our proton. Then we have lithium, which we talked about in the last lecture, where you lose 1 electron and you get helium's noble gas configuration. Beryllium, we know, is in group 2A, that forms a positive 2 cation that is going to give it helium's noble gas configuration. And so this is just our trend, and what we can start to see is that all of these ionic terms that we've known about since chapter 2 are because of electron configuration. So again, our periodic table is really telling us a lot, and yes, it was awesome to learn those trends with ions, but now we can start to use that same knowledge of the number of electrons in the valence shell, which again is going to be involved in bonding, to start to predict the shape of molecules, or the orientation of atoms to each other in a molecule. And the way that we do that is with Lewis structures. Sometimes they're called Lewis dot structures. That means the same thing. So if you're looking for possible videos on YouTube or something to complement these, you might find some good ones under Lewis dot structures. I'm sure they'll come up anyway. So here's an example of a Lewis structure with ionic compounds. So here we have lithium, and it's drawn with just that single dot. This single dot is representing 1 electron. Fluorine, we know, is in group 7A. That's a halogen, so it's 1, 2, 3, 4, 5, 6, 7. That is 7 electrons. We know that fluorine is going to seek to gain 1 electron in order to become like the noble gas neon. Lithium is going to seek to lose 1 electron in order to become like the noble gas helium. And indeed, that's what we see here in this Lewis structure representation of an ionic compound. Now, I'm going to be perfectly honest with you. I've never in my life used a Lewis structure to represent a ionic compound. I'll never ask you to do it. But it's cool to see that this is essentially the relationship that we have. And remember, bonding occurs because we have a lower potential energy. The system becomes more stable. The system has less potential energy. We talked about this bond in our last lecture. So we have 2 fluorines, 7 electrons in their valence shell, right? We looked at it as our orbital diagram, but now we can just simplify it and think just about the number of electrons in our valence shell, and we know that that correlates to our column of the periodic table. So when they bond, notice we have that sharing of our electrons here. So what's really important about that is that those 2 electrons are going to count as 2 electrons for each of the atoms that they're being shared by. So how we represent that, it's not actually represented this way. This is just an illustration. But this is how we would draw the Lewis structure for fluorine. the diatomic, heteronuclear diatomic molecule. Homonuclear. Oof. Homonuclear diatomic molecule. I know you're all thinking that. You're like, gosh, Sam. Okay, so this sharing of an electron is drawn as a single line. That single line is representing two electrons shared by the two atoms that it connects. So each fluorine came in with 7. And now, by sharing those 2 electrons, this fluorine would own, or we can think about it as having around its nucleus 1, 2, 3, 4, 5, 6, 7, 8, right? Because it counts as 2 for it. That would be 8 electrons. That would complete that fluorine's octet. This fluorine has 1, 2, 3, 4, 5, 6, 7, 8. It also has a complete octet. So if all of the atoms in the molecule have a complete octet, or we'll see a couple exceptions to that rule, then it's going to be at a lower potential energy, and we know that it is a viable structure. Okay, so here's a couple rules, and then we're going to do a ton of examples. So this octet rule is what I was just talking about. So atoms bond to achieve noble gas configuration. Noble gas configuration for the vast majority of elements is going to be a complete octet, right? They want to have 8 valence electrons. This is a really big consideration here, that the second row of the periodic table is never going to exceed an octet. So those elements that are lower than the second row of the periodic table are unique in that they have d orbitals that they can hybridize. Now we're going to talk about that a little bit in chapter 9. That's actually most of the material that we cover in chapter 9 is hybridization. So don't focus on that right now. Just know that if you're at n equals 3 or more, so let me just rewrite that. If it was n of greater than or equal to 3, it can exceed an octet by using empty d orbitals. So remember, when we're doing our electron configuration and we start going through those transition metals, we drop down in our n level from whatever our s orbital would be. So if it's like 4s2, it would be 3d10. So those 3d orbitals can actually be used by any n greater than or equal to 3, and d orbitals can be used to form bonds. So we'll see some examples of that, but in general, the vast majority of the elements that we're working with are not going to exceed the octet rule. So the duet rule is a pretty logical exception, and that is that hydrogen and helium only need a duet. They do not need an octet. That makes sense because both hydrogen and helium, right? So this would be hydrogen, this would be helium. They only have a 1s shell. They do not have any other orbitals that electrons are going to be occupying. So one thing that I like to say and always remind students of with hydrogen, basically the only thing that you will ever do with hydrogen is draw a single line from it to something else, right? Anything else. R would just be the rest of whatever you're looking at. Because that would be a complete duet. So exceptions to that is boron and beryllium will often form 6 bonds. And that's just one of their qualities. They're pretty tolerant of being somewhat electron poor, and it's just one of those, and I feel like every rule has to have an exception, right? So boron and beryllium will often have fewer than 8 electrons. Usually it is going to be 6 valence electrons. So that's just an exception to the octet rule. And then again, the third row and more, third row plus, can exceed the octet rule by using FDD orbitals. And so then the last thing that we want to look at is if you have a single bond, that's going to be 2 electrons, but you also have multiple bonds. If you have a double bond, that is representing 4 electrons that are shared between those 2 species. And if you have a triple bond, that is representing 6 electrons. Okay, so let's get some practice in. Yeah, I'm going to go ahead and use this program because I like it a lot more. Okay, so let's start with a molecule that we're already pretty familiar with, and we'll actually see why I've been drawing water the way that I've been drawing it for so long. So we have H2O. Very cool. So H2O is wildly important for organic life and for the chemistry that we've been talking about all semester. So what we want to do is be able to represent this molecule. And the system that we use, again, is called Lewis structures. And you're going to have to get really good at drawing Lewis structures. So the chapter 8 and chapter 9 recitation packet are identical. They are just working through Lewis structures. So I really encourage you to get started on those as soon as possible. And drawing Lewis structures are all going to follow the same flow. So the first thing that you do is you're going to sum your valence electrons. Okay, so that's going to come straight from your periodic table and looking at the group or the column that that species is in. So we have 2 hydrogens, and I look at my periodic table, hydrogen is in group 1A, so it'd be 1. I have 2 of them. So I have 2 valence electrons coming from my hydrogens. My oxygen is in group 6A, so that's 6 valence electrons. Oh, sorry. So then my total would be 8. Right, 6 plus 2. Okay, so I've summed my valence electrons. Then the next thing you do is you want to connect your atoms using, or let me say by. So connect atoms, yeah, with single bonds. Okay, so remember, a single bond represents equal sharing between species. So what's really important in number 2 is you have to, this is kind of like a subset, so let's just call it A. You have to identify your central atom. Okay, so what is your central atom going to be? Typically, your central atom is going to be the unique atom. Or element, right? So in this case, oxygen would be my unique atom. Other times, it's going to be your least electronegative, right? Following that trend that we talked about in the last lecture. And then finally, we have this consideration of it just being carbon. Carbon likes to form a lot of bonds. If you have carbon, chances are it's going to be your central atom. Okay, so in this case, we have water. So we'll draw out our oxygens. And the first thing we need to do is just create this like skeleton. Like, how are these things even connected? The only way that we can have this molecule is if there's at least bonds between all of the species or all of the elements involved. So now we've accomplished that. Remember, this is one line. Single bond represents 2 electrons, so that's 2 4 electrons used. So it means that we have 4 electrons left. So in the third step, you're going to calculate your remaining valence electrons, that's what we just did, we have 4 left, and use them. I'm sorry, this tablet is terrible. So you're going to use them to either or actually, let me back up. So you're going to use them to complete octets or duets, but duets never really happens. As soon as we drew this line to hydrogen, it was happy. So you're going to use them to complete octets. And the way that you're going to do that is first you see if you can do it by drawing lone pairs. And I'll explain what those are in a second. And the other way is by drawing multiple bonds. Okay, so let's talk about lone pairs. So remember when we were going through our orbital diagrams, we always have 2 electrons in our boxes when they have to be together, right? So if we're completing octets by bonding, it makes sense that you're going to have all of your electrons be together, right? You're completing those s and p orbitals. So it kind of makes sense that if you're going to have electrons, they're going to be traveling together, right? They're occupying that p or that, they're occupying that p orbital. So lone pairs are always going to be 2 electrons not shared in a bond. Right, so they're not forming a bond. And they're going to be used to complete our octets. So here we have our hydrogens are happy, right? So both of my hydrogens have a duet. My oxygen, however, at this point in the game, it has only 4 electrons assigned to it. So it is unhappy, right? Look at how pathetic that smiley face looks. So hydrogens are good, but oxygens are not. So I'm going to first see if I can satisfy my octet by using lone pairs. So I would draw them, right? You're kind of doing like a little guess and check here. So I have 4 electrons left. I can use that as 2 lone pairs, and now my oxygen has 1, 2, 3, 4, 5, 6, 7, 8. So now oxygen has 8, hydrogen has 2. So remember, this single bond counts as 2 electrons for hydrogen and 2 electrons for oxygen, right? By sharing, they have twice as much as they would have apart, right? Okay. So that's why I've drawn oxygen that way, that's why I've drawn our water molecule that way. And just to tie things back in to what we learned in our last lesson, you can see that oxygen has a lot more electron density around it. So the electrons shared in this bond are going to be between our oxygen and hydrogen most of the time, right? Because they're experiencing that attraction to hydrogen's nucleus and to oxygen's nucleus. Our oxygen also has these lone pairs, so that's a lot of electron density. So if we were to be drawing our dipole, I would draw those electrons being pulled from our slightly positive hydrogen to our slightly negative oxygen on both sides. And so we could think of that as being a net polarity, right? If we combined those vectors of that molecule having its positive and negative pole, this would be a polar molecule. All right, so it's a polar molecule. We don't have that like cancellation of dipoles. All right, so let's do like a at least 4 or 5 more examples. If that makes perfect sense to you, then you can just not watch the rest of this video and start doing some practice on your own. We'll have a couple more nuances, but you could speed it up. What's another one I want to do? Let's do, yeah, let's do SO3. Yeah. Okay, so sulfur and oxygen are both in the same row of the periodic table. So sulfur is going to be bringing its 6. Oxygen is going to be bringing 6. 6 times 3 is 18. So we have a total of 24 valence electrons. So I've done number 1, I've summed my valence electrons. Now I'm going to connect my atoms with single bonds. So we have sulfur connecting to oxygen. So that's 2, 4, 6. So I have 18 valence electrons left. So now I want to ask myself, can I use the rest of those valence electrons just to complete my octets? So right now I have 2 electrons assigned to oxygen, which means I have a deficit of 6 here, deficit of 6 here, deficit of 6 here, and a deficit of 2 here, right? So each oxygen has 2 electrons assigned to it, and my sulfur has 2, 4, 6. Needs 8, so it must 2. So the total there would be 20 electrons, which I don't have. So that's one way to think about it. That's the way that I kind of quickly do it. Alternatively, you can just draw on your lone pairs and kind of guess and check. So you draw on your lone pairs and you're like, okay, well, everybody's happy now. Everybody has a complete octet, but that's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. All right, well, I use more electrons than I have, so I cannot satisfy octets with lone pairs alone. So now we have a new situation where I'm going to have to use multiple bonds. So with the multiple bonds, first you start with a double, and then if you have to, you'll go to triple. That says triple. Okay, so let's just throw in a double bond here. So now I have 16 valence electrons left. But now I've also accomplished a couple things. So my sulfur now is happy. So that's 2, 4, 6, 8. It has a complete octet. Love it. This oxygen now only needs 2. So it has a deficit of 2. And this has a deficit of 6 still, deficit of 6. So that is a total of 16, which lets me know that all I have to do is draw on my lone pairs and I'm going to have my complete octets. 1, 2, 3, 4, 5, 6. Yep. I got carried away. All right, so once you're done, you always want to kind of double check your work. So I have 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. So make sure everybody has an octet. I use those 16 valence electrons. I have 0 left, and I have a viable Lewis structure. All right, let's do another example. Yeah, let's do ammonia. All right, so my nitrogen, group 5A, so that has 5 valence electrons. My hydrogen is 1 times 3 is 3. So that means that I have 8 valence electrons. So hydrogen would be my unique, or sorry, nitrogen would be my unique atom. It's 2, 4, 6. So as soon as you draw a line to hydrogens, they're done. If you ever draw a Lewis structure that looks like this, something is very wrong. Stop and start over. Right? Because it only has capacity for 2 electrons, which means that it can either have a lone pair or it can have a single bond. Okay. So I have this single bond, these single bonds using up 6 of my valence electrons. my nitrogen only has 6 electrons. It wants 2 more. I have 2 more left. And this is the Lewis structure for ammonia. All right, let's do another cool one. What else? Oh yeah, so let's do one that exceeds the octet rule, just so we can see what that looks like. So let's do PCl5. Okay, so we have phosphorus. That is in group 5A, so it has 5. Our chlorine is a halogen, so that's 7. I have 5 of them, so that's 35 total, which means that I have a total of 40 valence electrons. Now I need to connect my atoms with single bonds, and my central atom is going to be my phosphorus. So you want to just kind of get in the habit of trying to position your atoms like spokes in a wheel, kind of equidistant from each other. It's going to make more sense as we continue on with today's lecture why that's kind of important. Okay, so here I have my phosphorus and I have the chlorines. That's 2, 4, 6, 8, 10. I've used 10. So I have 30 valence electrons left. So here I would have chlorine has 2 electrons. It wants 8, like everybody. So I have a deficit of 6. 6 times 5 is 30. So I'm like, yay, I've done it. Again, if you like hate that method, you can just go ahead and be like, okay, what happens if I just make everyone have a complete octet using lone pairs? And you count up 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. Cool. Yay. So if you notice, all of my chlorines have a complete octet. My phosphorus has exceeded my octet. It has 10 electrons that are assigned to it, but it's greater than n equals 2. It's in our n equals 3, so it has those d orbitals that it can use for bonding. So this is a completely acceptable Lewis structure. All right, so this is cool. We're starting to get a feel for this kind of geometry and the makeup of so many of the chemicals that we've been talking about throughout the class. So speaking of so many chemicals we've been talking about throughout the class, let's go ahead and do some diatomics, right? So we're talking about hydrogen, H2. Each hydrogen is 1. You have 2 of them. So this is really the only makeup that we possibly have for our hydrogen diatomic. Now let's do our oxygen diatomic. So oxygen has 6. 6 times 2 is 12. I've used 2, so I have 10 left. Both of my oxygens would need 3 sets of lone pairs, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I don't have that many lone pairs. So I know that I have to use I have to use a multiple bond. So you always start by checking if a double bond will do ya. So now I have 8. Each of my oxygens needs 2 lone pairs. I use 2, 4, 6, 8. So this is my Lewis structure for oxygen, my diatomic molecule. Let's do one more. N2, each nitrogen is 5. 5 times 2 is 10, right? We love this chapter. It's simple math. So N connecting them gives me 8 left. Each one of these wants 6. Obviously, that's not going to be enough, so I'm going to go ahead and draw my double bond. Now I have 6 left. Each one wants 4, right? Because this is a double bond. So single bond is 2 electrons to each atom that it connects. A double bond is 4 electrons to each atom it connects. And a triple bond is 6 electrons to each atom it connects. So now we're going to try that. Now I have 4 electrons left. Both of my nitrogens have 6 that are ascribed to them, so they both just want 2 more. And this is the Lewis structure in the makeup of nitrogen. So this physical structure, this really strong bond between our nitrogen, is the reason why nitrogen fixation is so important on this planet, and the only species, or the only things on our planet that are able to fix nitrogen, which means to break this bond, is bacteria and legumes. So pretty cool. We can start to understand the way our planet functions, the way our bodies function, the way the world functions when we start to understand things on the molecular level. Okay, so coming back to our PowerPoint, oops. Okay, we have this. Let me get rid of this guy. My apologies. We have a couple additional, get rid of it. There we go. Additional considerations when we're looking at our Lewis structures. And one of them is resonance. So resonance is really getting at the fact that electrons aren't really assigned to any one species, right? We have this electron cloud, really, is what we can think of for electron movement around the atoms involved in bonding. So when we draw our Lewis structures, it's like we're assigning those electrons to the species, and it gives us a great understanding of our dipoles. It lets us predict chemical behavior. But it's important to recognize that following the rules of Lewis structures, sometimes you're going to get yourself into a position like the one shown here, where you could draw a Lewis structure and have it be valid many different ways. So this is a pretty simple example, and that's the only ones that you'll really be asked to evaluate. So here we have our NO3, and you can, this is a symmetrical molecule, so when you look at it, you could draw this double bond to any one of those oxygens. And what we see in our resonance structures is that all 3 of these kind of combined make describe the physical behavior, or the physical makeup of this molecule. So when we look at our resonance structures, their aggregation is actually the best. So this would be like equal electron sharing. So each one of these bonds has like some double bond character. Now you don't need to know this. What you do need to know is that resonance is possible, and there's multiple ways to draw a species. And the reason why is because electrons aren't fixed things. So in organic chemistry, we're always kind of drawing the movement of electrons. So let's go ahead and look at what species would I want to do? Yeah, so let's do acetic acid. Okay, so I would never ask you guys to draw this yourself. Everything that you're asked to draw for Lewis structures is going to have a central atom. So this is a little bit more advanced, but it does a great job of showing this movement of electrons. So one thing that we know is that this is an acid. Oh, we're going to go back to that other program. Yeah. Oh, twos. Oh, come on. All right. Oh, sorry. There we go. Let me just get rid of all this stuff. All right, sorry about that, guys. All right, so we have acetic acid, all right? So we have our carbon. All right, and this is what our acetic acid would look like as far as its Lewis structure would go. Now we know that this is an acid, which means that if this were in water, it's actually going to have this form. So those bonds that were held in, or those electrons that were held in that bond are given to oxygen. You just have this proton floating around in your solution. So one really cool thing about resonance is when you have these double bonds, they have and lone pairs, they have the ability to like move around. So we can essentially think of these electrons as being able to kind of migrate around our molecule. And so in organic chemistry, you spend a ton of time moving electrons around. Now, that's not going to be something that you're expected to do in this class. Instead, it's going to be things like that example from your textbook where you have a symmetrical molecule and either, any one of these oxygens could have had the double bond drawn to it. What's really the kind of takeaway here is that electrons are not fixed. They don't actually belong to one species. They can move around, and multiple Lewis structures are possible for some molecules. Right? Not for all. You're going to have a situation where you have these double bonds and your single bonds. Okay, so that's resonance. And before we get too much further, I do just want to teach you about a little trend that can make drawing Lewis structures a little more predictable and a little more quick. So, let's bring it back to this slide for a second. So if we were looking at the Lewis structures that fluorine, chlorine, bromine, and iodine typically form, you're going to see, okay, fluorine, the diatomic, looks like this. Chlorine looks the same way. Right? They all have 7 valence electrons that are assigned to them. They have this tendency to form one bond. I like to remember that because they are one step away from a noble gas. So group 7A is going to have a tendency to form one bond. Right? So here's our examples. Now group 6A, we just did an example there, is going to have a tendency to form 2 bonds. So our oxygen bound to itself in the diatomic, or water. Right, so it could be a double bond or it could be 2 single bonds, but also notice it is 2 steps away from a noble gas. And you still need to do all of the other steps for Lewis structures, but this is a really nice way to kind of look at what you've got and ask yourself if it makes any sense. So group 5A, we're going to see typically has 3 bonds, right? We just saw that with our diatomic nitrogen. Now we also know that ammonia is really common. So 3 bonds. Yeah. So, and here we're 1, 2, 3 steps away from our noble gas. Now we have group 4A is going to have a tendency to have 4 bonds. And now this is very much true of carbon. Carbon wants 4 bonds all the time. So example would be, let me get rid of that, sorry. methane. Another example that we've already seen would be carbon dioxide. Another example would be carbon and amine, like this. So we have a triple bond and a single bond. So those are all possible configurations. Obviously, there would be different elements that carbon is bound to, but notice carbon likes to have 4 bonds. Everything in the 4A is going to follow that same trend. So again, same column, same bonding trends, same chemical trends. Ooh. Okay. So resonance is this idea, electrons can move if you have double bonds and lone pairs and you draw a Lewis structure, and there's 2 different ways to draw it. Just ask yourself if you're following all of the rules of Lewis structures. Is this just a resonance structure? Okay, so formal charge is another big concept. And formal charge is something that we're only capable of figuring out when we draw a Lewis structure. So here's a Lewis structure that is drawn for you, and this would be pretty indicative of the kinds of questions that I would ask for formal charge. So formal charge is going to be equal to the number of valence electrons that that species typically has minus the number of electrons assigned to it. Nope, sorry. Let me let that go away. It's the other way around. So formal charge is the number of electrons assigned to it in the Lewis structure minus its number of valence electrons. Okay, so here we have a species, and if we wanted to know the formal charge of nitrogen, so for formal charge, you're always just looking at one element in a molecule. So nitrogen's valence electrons is 5. And here it has 1, 2, 3, 4, 5. So its number of assigned is 5 minus 5 would be 0. So its formal charge is 0. I do the same thing for my oxygen. Right? Oxygen typically has, or oxygen's valence electrons is 6. Here it is 1, 2, 3, 4, 5, 6. That is 6 valence electrons. 6 minus 6 is 0, so it has no formal charge. So this molecule has no formal charge, which is really cool. Now, you can also have a resonance structure of this, right? So this would be a resonance structure, so you could just as easily have done all of the steps for a Lewis structure and ended up with this molecule. So if you've drawn a molecule and you're not sure if you did it correctly, a great method is to go back and look and calculate what the formal charge of your species is. So here, if we look at this oxygen, it has 1, 2, 3, 4, 5, 6, 7. 7 electrons assigned to it. It has 6 valence electrons natively. Minus 7 would be -1, and we symbolize that with this negative in a circle. Now our nitrogen here has 1, 2, 3, 4. So it has 5 assigned to it minus its, 1, 2, 3, 4. So it has 5 valence electrons natively minus the 4 that it has assigned to it, and you get a +1. So we show that with that positive symbol. Now notice the sum of your formal charges must equal the charge of the molecule. Right, so in this case, this isn't a charged molecule. It's not ionic in any way. So it's not like a polyatomic. That would be an example of a covalently bound charged ion. So those formal charges need to balance each other out. Now you could also draw it this way. However, you know, our carbon doesn't have a complete octet, so it makes sense that this would be very minor. So these are all resonance structures for this species. This is going to be our major one. So the vast majority of this molecule that you were to find and isolate would have this structure. A very few number would have this, and then a minuscule amount. This would be very, very fleeting, right? Because carbon likes 4 bonds. So another thing that I like to look at with formal charge is I think about that trend that I just showed you with the columns of the periodic table and seeing how many columns away from the noble gas it is. And like we know that nitrogen is 3 steps or 3 columns away from our noble gases, and here it has 4 bonds. So that's a good indication to me that that's going to have a formal charge. So you just want to get some practice with that. So again, remember that's going to be, so formal charge is the number assigned, the number like native, right? So that's going to be from the periodic table minus the number assigned in the Lewis structure. Cool. So the most likely resonance structure is going to minimize the number of formal charges, right? Because all of the elements are kind of bonded in a way that correlates with their chemical structure and behavior. Okay, so this has been a lot. You can pause the lecture here and like get some practice, because this next step is kind of a continuation of what we just did, which is looking at Lewis structures in order to determine molecular geometry. And that all has to do with this valence shell electron-pair repulsion theory or model. So the valence shell electron-pair repulsion model is looking at the fact that in your valence, you have a lot of electrons. Those electrons are going to be repulsed by each other. And so the most likely orientation of the molecule, or let me actually just say the geometry of the molecule, will minimize electron repulsion. So this model explains why when we draw ammonia, this is the way we draw it. So ammonia is NH3. When I drew it before, I didn't draw it like this, which would put those hydrogens as far away from each other. I drew it like this, because this actually allows for the least electron repulsion. So we'll go through a lot of examples, so let's not stress it. So here we have our 2 very important concepts with our very familiar H2O molecule. So here we have H2O. This is another way that you could draw the Lewis structure of H2O, which would just be, but this is actually, as I show here, it's not the best way to draw it. So water, that's how you've seen me draw it all semester, and the reason why is that it is minimizing repulsion. very cute. So he's a puppy. He doesn't know any better. I'm sorry. So here we have our oxygen. It's bonded to 2 hydrogens, and then you have the 2 electron pairs that belong to it. So we have this concept of electron geometry and then molecular geometry. And there's going to be a lot of new vocabulary that you're going to need to learn. You just need to create like a table for it in order to describe these 2 different forms of geometry, or the names of their geometry. So electron geometry is treating everything as equal. So it doesn't matter if it's an atom or an electron pair, right? Otherwise known as a lone pair, right? These are lone pairs. So electron geometry, we don't care if those electrons are in a bond or if they're kind of free and assigned to just one of the elements. But here you can see like there is a difference, right? So we have lone pairs and we have our bonding pairs. And actually these lone pairs, you want to think of them as having like a lot of room to roam, right? They're not confined to an area where they're attracted to 2 different nuclei like they are between oxygen and hydrogen. So they're able to exert a force, right? Their repulsive force on each other is going to push the bond between our hydrogen and our oxygen. It's going to shrink this bond angle. So it's going to push it down in order to create more space for those lone pairs. And so here our electron geometry, and we're going to get to this, is called tetrahedral. Our molecular geometry is bent or V-shaped. I don't care which one you use. Your book uses V-shaped. A lot of other resources use bent. Don't care which one you use. They mean the same thing. Okay, so let's just think about this in terms of the number of atoms that something's bonded to. So we think of those bonds as your like effective electron pairs, right? So in this example, let's say this is our carbon dioxide again, right? So this would be a linear geometry. So this is our geometry. And you guys need to know all of these terms as well as our angles here. So linear would be 180 degrees bond angle. So one important thing, so this is our number of electron pairs around our central molecule. So you're always kind of counting. I like to think of it as the number of things, right? Or effective electron pairs around that central atom. So number of things could be, so a thing is going to be a lone pair, or it's going to be any kind of bond. So that means single, double, or triple bond. It doesn't care. It doesn't matter. So for this linear arrangement, if we have carbon dioxide, right, that's going to be carbon has 4, our oxygens have 6, times 2 is 12. So that is 16 valence electrons. Carbon likes 4 bonds. Let's just count them up. That's 2, 4, 6, 8, 10, 12, 14, 16. This is the Lewis structure of carbon dioxide. You're not going to be that fast. I've been doing this for years. It's great. So notice when we are talking about our geometry, I'm looking at this carbon and I'm saying that there are 2 things about it, around it. I don't care that it's a double bond. All that matters is that I have 2 atoms that are around it. For my oxygens, I would say that they have 3 things around it. So each oxygen has a double bond and 2 lone pairs. So that's 3 things. But we care about our carbon, right? Because we're always going to be evaluating that central, the central atom in a molecule. At least for now, in chapter 9, that'll change. So this is linear. There's actually a couple examples in this chapter, but the structure will be given to you. Okay, so here we have another molecule, and this is our central atom with 3 atoms equidistantly spaced around it, and this would have a bond angle of 120 degrees, right? This is 180, that one's 120. The next one we have is tetrahedral, so that is 4 things around it. Example there would be CH4. The carbon diamond figure that we had at the first slide of the chapter 8 lectures was all carbon atoms in this tetrahedral arrangement. So notice this is 2 things around it, 3 things, trigonal planar, 120 degrees, model, 4 things, tetrahedral, there's our model, this would be 109.5. Then we have trigonal bipyramidal, so notice I have 1, 2, 3, 4, 5 things around it. And this is where you're going to get, you're going to have a little bit more tricky angles to work with. So let me just work with this model I have really quickly. Okay, so this would be like my trigonal bipyramidal. So we have our trigonal planar with 3 things. And that is really like the core of our trigonal bipyramidal. So this would be our trigonal planar. Trigonal bipyramidal, we just have on either end atoms attaching. All right, so you have a triangle, 2 pyramids. You can think of each side as being a pyramid. So it makes sense that here we have a 90-degree angle, and here, here we have a 90-degree angle, and here we have 120. So those are kind of mixed angles. They're going to be depending on which orientation you're looking at. So octahedral, which I don't even know if I have. I don't have one of those. Octahedral is going to be where you have 6 things around your central molecule. So we have 6 things. This is our example. So octahedral, 6 things. Each one of those things you can see has a 90-degree angle. All right, so the way you're going to use VSEPR structures is by first drawing your Lewis structure and then figuring out what is my electron geometry and then what is my molecular geometry. Okay, so the difference between electron geometry and molecular geometry is that molecular geometry is taking into account the effect of lone pairs on the overall geometry of the molecule. So to predict a VSEPR structure, you start by drawing a Lewis structure. You put lone pairs and bonds as far apart as possible. You determine the number of things around the molecule. And then you consider the effect of lone pairs. So this is just really an extension of the Lewis structures that we were just drawing. So if it's linear, it's pretty straightforward. 180 degrees. Very cool. Another example of a linear molecule would be like HCl, right? Linear. Then we have our trigonal planar. where you're going to have your, you have your central molecule and 3 things around it. So we did an example earlier. It was SO3. Right? This is trigonal planar. Now, as soon as you start getting into tetrahedral, you're going to have some situations where you need to take into account the effect of those lone pairs on your overall geometry. So here we have our central molecule and the 4 things around it. If all 4 of those things are atoms, then your electron geometry, I'm just going to abbreviate that as EG, is going to be tetrahedral. And your molecular geometry, MG, is going to be tetrahedral. If one of those things is a lone pair, so your lab is looking at these kind of situations. One of those things is a lone pair. Your lab is going to have those lone pairs drawn in. Then you have a situation where it's trigonal pyramidal. So example there would be our NH3. This is trigonal pyramidal. Those hydrogens are pushed down towards each other more than you would have with a trigonal planar because the lone pairs want to create or want to minimize those electron repulsions from each other. And then last we have our bent. That's 2 lone pairs around our central molecule. Still it has 1, 2, 3, 4 things around it. Its electron geometry is going to be tetrahedral. All of these have a tetrahedral electron geometry, but its molecular geometry is bent. For this one, tetrahedral. I just misspelled that. No, I didn't. And then the molecular geometry is trigonal pyramidal. You can say pyramid or pyramidal, I don't care. Most other textbooks say pyramidal. Okay, once we get into 5 things, then you have even more terms to know, right? Because we have more opportunities to have lone pairs be a thing. So if you have 5 things and all of those things are atoms, we've already seen this, it's trigonal bipyramidal, right? Here's our triangle and our 2 poles for our pyramids. If one of those things is a lone pair, then we have seesaw, right? Electron geometry, trigonal bipyramidal. Molecular geometry, seesaw. 2 things are electron pairs, then it's T-shaped. 3 things, electron pairs is going to be linear. And that makes sense, right? So going back to this molecule, if we had 3 lone pairs, that would be the structure, the orientation of the atoms to each other. So pretty cool. We have one more. Okay, so I actually want to add something. Your textbook doesn't have a figure for this, but then I asked you questions about it, so let's just go ahead and talk about it. And that is going to be octahedral, right? Which sounds like I just like spit up a little bit, but it's if you have 6 things, this is octahedral. So octahedral, 6 things, right? And we saw this not too long ago. So you have kind of this square with 2 poles, so octahedral. Now, if one of those things is a lone pair, so let's say this guy was a lone pair, then it's called square pyramidal. If you have 2 lone pairs, it is called square planar. And look at the lab, and it kind of walks you through each one of those. So You need to know the bond angles for, this would be our tetrahedral is 109.5. This would be our trigonal pyramidal is 107. And then our water is 104.5. Now, your textbook also just calls this less than 109.5, which I'm fine with. So these are your bond angles. And remember that VSEPR structures are really just an extension of our Lewis structures. So single bonds, double bonds, triple bonds all count as one thing. Electron geometry doesn't take into account the effect of lone pairs. Molecular geometry does. And that distinction is going to be made really clear in the lab. This is a really nice table I put together. I think the first semester I was teaching. It's a little overwhelming, but it does a good job of showing you examples of each of the geometries that we talked about, including square pyramidal and square planar. So I encourage you to draw each one of these out.